Well, we'll start in about 15 seconds. And it's time. Looks like it's just you today, Clay. Thanks for making it in. Any questions at all before we get started today?
No, I'm just kind of tired. I took the math quiz today.
Awesome. Glad to hear that.
Hopefully, Heidi.
Awesome. Well, for what we're doing today, we have the quiz 7 due today. The new quiz number 8 is posted, and we're working through section 7.6. Also, I'm going to be grading the exam 2 over this Friday. And once all the exams are graded, I'll be sending everyone the graded copy of the second exam. And we're getting pretty close through the rest of the material. This is week number 9. There's only 15 instructional weeks. So at the end of the 10th week, next week, we're pretty much 75% through the entire semester. So definitely getting through it. So here's where we left off last class. Here we're solving in the last section for chapter 7, rational inequalities. What we mean by that is there's an irrational function, that's the x plus 2 divided by x minus x plus 8. It becomes an inequality when we have something like less than, or greater than or equals, or less than or equals, like in this problem. And the ideas to solve this are really pretty much 3 big steps. The first step that we do is we look for either, we call these a critical point.
Finally got more people.
Excellent. Thanks for making it in, folks. The first step we take is find either the critical point or the cut point. So this is really step 1. And thanks for making it in, folks, like Clay was mentioning. The cut points or critical points are really just found by doing 2 things. You first find the excluded value. But from section 7.1, an excluded value is what makes the denominator go to 0. It's the value that's undefined. So we took the denominator, set it to 0 and solved, and we got one excluded value. So that's one cut point. The other cut point is just found by making the numerator equal to 0. So we took x plus 2, set that one to 0 and solved and got the negative 2. And so that's pretty much step 1. If you say this as one big summary, you just take the top and the bottom, set them both equal to 0 and solve. Just keep in mind the bottom set equal to 0 is what gave us the excluded value. So after we did that, the second step is the test points. So this is step 2. We write down the number line like we see here. We put in the 2 cut points, -8, -2. And now we're just testing the sign, whether it's going to be positive or negative, in this entire region going left to -8. The thing that we're testing in is the x plus 2 divided by x plus 8. Throw in any number to the left of -8. -9 did the job, and we plug -9 inside here. So that's why we got to -9 plus 2 divided by -9 plus 8. It came out positive, so we just put a positive sign in this entire region. So this bracket says, to the left of -8, it's always positive. Likewise, when we put in a -3, here's our test for -3. It came out as -1/5, so negative. So it's negative in this entire region. And we tested a value of 0 and found it's positive in this entire region. Then our step 3 is to shade the correct region. In other words, we're deciding, do we want the positive regions or do we want the negative region? It all just depends on this inequality sign right here. If it says less than or equal to 0, that means negative values. So we wanted the negative regions. If this was instead something like, say, x plus 2 over x plus 8, and it went greater than 0 or even greater than or equal to 0, then this would mean we want the positive regions. So watch for the sign of the inequality. It's going to tell us what part of the number line we actually pick up. Because it was less than or equal to 0, we just wanted the negative regions. So we shaded this region. Now this is the graph for the entire solution set. And then in step 4, we just rewrote it in interval notation. So this is step 4. Interval notation. And this is how each one of these goes. We find our excluded values, we write down the cut points, do the test points, and then shade as normal. So it's a lot of work to get it all done, especially with all the notation. But practicing about 3 or 4 of these, it becomes pretty second nature. So this is the one we did right at the very end last Thursday, before going into the weekend. Any questions at all before we try out some new ones? Okay, actually part A was kind of a nice problem that we're looking into. What makes this one really, really excellent is the fact that there's a 0 right there. You take away that 0, then we have to do some algebra to bring it back. And it's quite similar to when we were, say, all the way back in section 6.5, the polynomial equations. Let's take a look at that for just a moment, just for the sake of seeing what we're about to do. So to make a big connection on some of these strategies, what makes equation solving nice in section 6.5 is when things are set equal to 0. It means you can break things down with the zero product property, set one factor to 0 or the other factor to 0. That was not helpful on this one. If there's a negative 24, the first step was to get 0 in the problem. And even worse on this one, when there's a 9, we had to FOIL this all out, move the 9 over until we got the 0. Then we could factor and set the factors to 0. So the 0 on one side is like one of these big critical things that we need in algebra, whether it's equation solving or inequality solving. And that makes that 5 right there by the red dot a big problem. If it was a 0 right where this is, it's just like part A. But with a 5 there, we have to do extra algebra, just like we had to do extra algebra on this problem. So let's put this one maybe on the next page so we can fit all the algebra on this one. So the very first thing we have to do before we get started on any of those steps we saw is get 0 on one side. We might as well write this in as an overall step. First, we want 0 on one side. And the next problem has that, so we're doing a slightly harder problem, and then we'll take a break on part C and see how this one goes. So first, focusing on this one, it's easier to get a 0 on the right-hand side, so I would just subtract 5 from both sides to start it off. It's now x minus 2 divided by x plus 6 minus 5. Give it a little bit of space. We're going to make some changes on the left-hand side. Is less than or equals to 0. So this starts it out. But after we get 0 on one side, the next thing we have to do is make this one whole fraction. We have to actually do the fraction subtraction right here. So next, add or subtract, depending on the problem. Here we're subtracting the fractions. And it's weird to use plural here to say the fractions because we're looking at one fraction, but you can always field promote any integer to a fraction as well. Now it's 2 fractions, and we have to add these together. Well, really subtract them. It's not so bad because this has a least common denominator, x plus 6. So this goes pretty fast. There's not going to be really complicated fraction addition or subtraction in this section. It's going to be something about like this. To get the least common denominator, just multiply by x plus 6 below and above. Now it has a least common denominator, and you can rewrite this as one fraction with that common denominator x plus 6, and then just subtract across the numerators. So the numerator is now x minus 2 minus 5 times x plus 6. Whole thing is less than or equal to 0, and we're just about there. We've added and subtracted the fractions rather. Next, simplify. this numerator here, and then we can get started on the problem as if it was just like part A. So all we're really doing is distributing the -5 inside and then combine like terms. So the numerator is now x minus 2 minus 5x minus 30 divided by x plus 6, set less than or equal to 0. And our like terms are going to give us x minus 5x for -4x, and then -2 minus 30 for a -32, divided by x plus 6, set less than or equal to 0. So that was a lot of work, but we're just about there. This is where the problem kind of starts in earnest with those steps 1 through 4 that we've listed out before. Very next thing we do is obtain the cut points. Before getting those cut points, any questions on the algebra to get it into the right format to start? Okay, like we were looking at for the first problem, pretty much the big punchline to getting the cut points is you just take the numerator, set it to 0 and solve, and you get 1 cut point. Let's do that. Solving this is pretty quick. Add 32 to both sides. -4x is positive 32. Divide by -4 into both sides. And x is going to be equal to -8. Let me double check that. I must be tired. This seems like a weird thing I'm looking at. Divide by 4 and it's at 8. Yeah. For some reason I felt like I really needed to double check that in the calculator, but we get a -8 altogether. So that's what one cut point x cannot be equal to, or rather x is equal to -8 for 1 cut point. I wrote not equals to because I got mixed up. This one's not an excluded value. Putting a -8 here is okay. You just get positive 32 minus 32, and the whole thing goes to 0, which is allowed. The one to worry about is for the second part. We set both the numerator and denominator equal to 0, and so now when you set x plus 6 to 0, we get x equals -6, but that one is the excluded value. X cannot equal -6. Just a reminder, it's not a bad idea to put this down on paper. This one is the excluded value. And that's our common acronym for excluded value, E dot V dot. So once we have the cut points, we just go down to the numerator and do, as the name kind of suggests, make 2 cuts, one at -8, one at -6. So we got them from setting the numerator denominator equal to 0. And here's our next step. 1 cut right at -8. Another cut at -6. Making 2 cuts on the real number line gives us 3 different regions. One's infinitely long from -infinity up to -8. There's a finite region from -8 to -6. And then another infinitely long region from -6 to infinity. What we want out of all of this is to determine what is the sign here, here, and here. Is it going to be positive or negative? Well, we're at the test point phase, so let's write it out. Copying the same color coding for what we did in part A, the test points means we're plugging in values inside -4x minus 32 divided by x plus 6. We just need to know what are good values. We can't use -8. I mean, -8, that's just going to make the numerator go to 0. That's neither positive or negative. We can't use -6 because that's dividing by 0 in our denominator. It's just undefined. We have to use values to the left of -8. Convenient one might be, say, maybe -10 or -9. Either would be a good choice. So come back over here. If x is -10, that means we're plugging -10 into this entire rational expression, just the left-hand side. We get 4 times -10 in the numerator, minus 32. -10 plus 6 in the denominator, when we drop it down there. Then we just simplify this as much as we need to in order to determine, is this thing positive or negative? So in the numerator, we have 40 minus 32. In the denominator, we'll get a -4. That means we have altogether 8 over -4, and that's less than 0 for a negative. So this entire region now, no matter what test point you picked, whether it was a -9, -9.1, anything along this number line, this entire rational expression is always negative. So we just put a big negative sign just to paraphrase that. That's one down, 2 more to go. Any questions about the first test point?
What the?
Okay, well, let's try this out again. Let me know if you have questions on this next one. The next one we're plugging in is a -7. Notice I'm trying to write these kind of small because our solution is going to involve the -8 and -6. And these are just the test values. Try to write them kind of light when you're doing them at homework so you don't get distracted by the main cutoff points, the -8, -6. We just do it all over again. We're plugging -7 here. So let me write, if x equals -7, then you'll get a -4 times a -7 minus 32. -7 goes down below here, so it's a -7 plus 6. So 2 substitutions in those 2 spots. Let me highlight this in green just to emphasize the values are going into those 2 spots when we pick those test points. We get another fraction. All we need to determine is if it's positive or negative. So this time it's going to be positive 28 minus 32. Divide by -1 in the denominator. That means this is -4 divided by -1. But that's a negative dividing into a negative. That means it has to be positive. This is just a +4 altogether. So that means in this entire region between -8, -6, no matter what number you pick, always positive. Then one more time. We just need a convenient number in this region. You might pick, say, -5. That would work. But you might have noticed probably the most convenient test point ever is 0. It's somewhere far to the right. But if I pick a 0, plugging 0 here is just going to give us the least amount of work. So let's go with the 0 whenever we can. If x is 0, then you'll get 0 minus 32, so just a -32 in the numerator. 0 plus 6, so just a +6. And it doesn't even matter what this comes out as. What is important, though, is that it's negative. It's a negative divided by a positive value. So it's less than 0 for negative. That means in this entire region, it's always going to be negative no matter what. At this stage, we're almost done. We just need to figure out which regions, the positives or the negatives, are going to be our solutions. We have to decide on solid dots or open circles and shade the right region. So it all comes down to this right here. Because this is a less than or equal to 0, we want negative regions. If it was a greater than or or equals to 0, that would have said a positive number, and we would have picked this region. But less than 0 means negative, so we go to the negative regions we see here. Our solution set is going to go to the left. It goes up to -8 and includes it. -8 is part of the solution. It would make it 0, and that satisfies less than or equal to 0. Nothing in here is going to work because these are all positive values, so we want negative altogether. And then at -6, we have to be really careful. This one is an excluded value, so there's no way it can be part of the solution. In fact, let's use the same color as before. Because it's an excluded value, we have to go in an open circle on this one, then shade to the right. So our solution set goes off in 2 opposite directions this time. And if we were to write that out in interval notation, it would be -infinity up to -8 with a bracket, union. Because this one's an open circle, we use a parenthesis to say -6 is not in the set. go from -6 to positive infinity. So there we have it, the total solution set. The set of all numbers that satisfies the original inequality goes from -8 up to, negative infinity up to -8, including that boundary point. Then starting at -6, but excluding the -6, every number larger is also a solution. Well, any last questions, folks, on getting through this kind of a harder one? I typed a Z there for no apparent reason. Let me delete that. That's a good question, Tracy. It depends on what's going on in the numerator. I think I have an example. Let me take a look at it below. This one might have more than one test point altogether, because when we go to set the numerator equal to 0, we'll get two different solutions. So I think typical is three test points because of the two cut points, but there could be some in the homework where it's going to be maybe 4 test points because we might get, say, 3 cut points, like on part D we'll take a look into. Other questions so far? Yeah, absolutely. Thanks for that question. I think in the next problem, it's going to be 3 test points again, but we should have a different one on the last part of the last problem for these notes. So let's give this a try. This was the harder one, so watch out for these. If there's a 5 on one side, you have to do a lot of extra algebra just to start it up so you can get the 0 on one side like this. That means the next problem is kind of like a mental break because it's all set up. We already have 0 on one side, so the problem can just start immediately. I probably would take just one additional step on this. It's helpful to have the denominator factored, so let's rewrite this as x plus 9. Divide by 3 times x minus 4. Factoring is always good practice, so when you can see something factors, it's a good strategy to take it. Now this problem is just ready to start. We have 0 on one side. Because this says greater than 0, it also means we want the positive regions. Let's go in order. Let's start off with the cut points. There's 2 cut points on this one. First one comes from setting the numerator to 0. X plus 9 equals 0 means x equals -9, and so there's 1 already. -9. Set the denominator equal to 0. 3 times x minus 4 equals 0. Then just use the zero product property. The only way that this equation can be true is if x minus 4 itself was 0. And that just means x equals 4. So the second cut point is a 4, but this one is the excluded value, because that came from setting the denominator equal to 0. It's less a danger, though. If this is a strictly greater than 0 or strictly less than 0, the fact that this is an excluded value is not as dangerous of a concept because we're always going to put a circle around the cut points. They're not the solutions guaranteed, both of them. The real danger with excluded values is when it's less than or equals or greater than or equals, because that's when you have one that's solid, but one that's blown open because it's an excluded value, which feels really tricky until we just were thinking about it from the very onset. So this one's a pretty friendly problem for a number of reasons. We already have the 2 cut points we need. We can jump right into the interval, or the number line rather. Let's make those 2 cuts, one at -9, another one way out here at +4. It means with 2 cuts, we have 3 regions. So 3 test points again on this one. And now we just pick out our favorite number to the left of -9, between -9 and 4, and larger than 4. So this is the test point phase. So again, kind of write these sort of small so we don't get distracted that -9 is the main part of the solution. And this is just an extraneous value for a short test. I think -10 is a good one to use in this region. So take x equals -10. We take that, plug it into the inequality up here, just the left-hand side, the rational expression. We have negative 10 plus 9 divided by 3 times negative 10 minus 4. Simplify this down just a bit. We have negative 1 in the numerator, 3 times negative 14 in the denominator. But the exact value of this is not as important as whether it's positive or negative. There's two negative signs here, so it's a negative value dividing into a negative value. That means the overall sign on this one is positive. So we're positive in this region. And you know, another pattern you might have noticed is they seem to alternate. On the very last problem, it went negative, positive, negative. On the very first problem, it went positive, negative, positive. So we might think that pattern is always true. It turns out that's false, though. There's a way to make it false. If for some reason it went like this, power 2, the signs can in fact repeat. It could go positive, positive, negative, negative. It's just the fact that on these problems we're looking at right here, these groups, the numerator and denominator, have powers 1 on them, that the signs do alternate. So if you were to save some time on this one, and you just put in a negative and a positive, that would work out on this problem. But if you have the extra time, suppose this is a quiz problem or an exam problem where it's higher stakes, it's a good idea to just double check, see if it really comes out to negative on the next region. So I'll do the checks just for the sake of extra consistency. And because this is a principle that doesn't always happen, the signs don't always alternate, it's good to just be extra cautious. So I'll pick on this one. Let me try to Control Z that, one moment. I'll pick in this interval between negative 9 and 4, the value 0. Set x to 0 as a test point, means plug it in to this spot and this spot, highlighted in green. We'll get just a 9 in the numerator and 3 times negative 4 in the denominator. There's just one negative sign this time, so this is a negative value, less than 0. So that means in this entire region, only negatives. Then one last one to go. But by the way, it looks like it's alternating like we saw. It's going from positive now to negative. And my bet is that this one will be positive. So let's plug in a 5 next. If x is 5, we'd be plugging 5 here. So now it's a 5 plus 9. In the denominator, it's 3 times 5 minus 4. Simplifying this new fraction, we have 14 over 3 times just a positive 1. So this is a positive quantity here. Right, greater than 0. And for greater than 0, that just means positive in this entire region. So that's our entire sign chart. Back over here, we have to decide which region did we want, the positive or the negatives. But because this is greater than 0, this means we want positive regions. If it was a less than 0 or less than or equals to 0, like in the last problems, that's when we would have switched over and said we want the negatives instead. But greater than 0 just means positive, just like how we said greater than 0 here and put a positive sign on this interval. So if we want the positive regions, that means we're going from negative 9 to the left, positive 4 to the right. It's a greater than, so on both of these, it's going to be an open circle. And the shading goes like this. Shading left in this direction, shading right in this direction. And so the inequality, the graph here goes into the interval notation form, negative infinity to negative 9 with a parenthesis, union 4 to infinity. And notice the other part of the pattern. Parts of our intervals always is going to be the cut points that we designated. That happens on every one of these kind of problems that we look into. Well, that one is a kind of a short and sweet kind of problem. We didn't have to do really any algebra. Factoring out of 3 was just for convenience to start it out. And that's how it kind of goes in the homework for this section. It's kind of a bumpy ride. Some of them are really quick like this. Other ones are like the prior parts or the very next one we're going to look into that does require some algebra just to get it started. So that's the one we're going to look into next, the one that requires a good amount of algebra. First, any questions with the one we just did? Okay, let's throw this one on the next page. So we're not trying to cram it in. So this one has multiple problems. The biggest problem, in my opinion, is the fact that there is not a zero on one side. Probably the easiest way to get a zero on this one is, you can just subtract x, subtract 1 from both sides, and get a 0 on the left. On every problem that we're looking at, we had 0 on the right, but that wasn't required. You can put 0 on the left, and that works just as fine. So let's go with that route, just for the sake of variety and looking at these. Subtract x, subtract 1 from both sides, and we get 0. Hang on, that's deleting on its own for some reason. Let me try to fix that. We get 0 is less than 5x minus 3 over x minus 3 minus x minus 1. So we just subtracted x and 1 from both sides. Now at this stage, we can go like this. We can make this be over a fraction, a 1. But in doing that, let's take one additional step. If I write down a fraction like this as it is, I'm going to erase these just a moment. So let me use this pen. If I write it like 1 like this, that's kind of a problem algebraically, because it now looks like you're multiplying both fractions together. We're not. You could put an additional addition sign right in the middle, and that'd be one way to fix it. Another approach would be you can write out one additional step and go less than 0 less than 5x minus 3 over x minus 3. Let's just factor out a negative sign from this entire group. You'll have negative x plus 1. Then make it over 1, and now it's less of an issue. We forced a sign right inside there. And really, there's two ways to do it. Either put a positive sign in the middle or a negative sign. It just can't look like something like this with nothing in the middle, because that's starting to indicate you meant to multiply the fractions when we really didn't. Okay, so now we have 0 on one side. It's on the left-hand side this time. We have two fractions. The least common denominator will be an x minus 3. So we just multiply this by what we want, x minus 3, which means we also need to multiply that into the numerator above. So we have the common denominator x minus 3. We can go 0 is less than that common denominator, x minus 3. We're subtracting across the numerators, so we'll copy in 5x minus 3 minus x plus 1 times x minus 3. Which means we now need to FOIL all this out, combine our like terms, and see what we get next. But we're getting there. This is progress. At least we've added the fractions, well, subtracted them. Any questions to this step? Okay, let's do maybe some scratch work on the side. We're going to need to multiply out x plus 1 times x minus 3. It's a nice factorization, but it's useless if there's other terms right around here. So let's unwiden this. FOILing out x will give us an x squared minus 3x. Distribute the 1 through, so get plus x minus 3. So this is x squared minus 2x minus 3. And then it has to be multiplied by a negative sign, so that'll be the next step. So 0 is less than 5x minus 3 minus, FOILing all this out gave us this result. Let's copy it in. X squared minus 2x minus 3 over x minus 3. It's still not quite there. We need to distribute the negative sign into the group. Let me move this up and over so we're not running out of all of our vertical space. So I have 0 less than 5x minus 3, and now just multiply that negative sign into the group. Now it's negative x squared plus 2x plus 3. When we distribute in the negative, all we do is we flip all the signs we see inside the group. It's all divided by x minus 3, and we're getting there. 0 is now less than. Let's combine our like terms. We have a negative x squared, 5x plus 2x, so plus 7x. And the positive and negative 3's do cancel out, so that's a nice bonus, over x minus 3. And if you really wanted to, notice you can leave the 0 on this side, or you can just flip this all around if you prefer. Let's actually flip it around just to see it from a different point of view. Another thing you can also do as well is you could factor out a negative x from this numerator. So if I factor out the negative x, that leaves behind positive x minus 7 over x minus 3. I'm flipping this around. It has to point towards the rational expression, open towards the rational expression. So we have greater than 0. And I'm noticing one mistake I made from the very, very beginning that carried all the way through. No worries, we don't have to change our work, thank goodness. But that was less than or equals to 0. So that means it should have been less than or equal to 0 all the way through until the last step, we flipped it to greater than or equal to 0. That was a weird thing to forget. But we got there, folks. Finally, we have a rational expression. Next thing we want here are all the cut points. The cut points are going to be, we set first the numerator equal to 0. Negative x times x minus 7 equals to 0 is just a zero product property problem. One way we get this solved is if x is 0, or x could be a positive 7. So those are the two solutions right away for cut points, 0 and 7. Next, we set the denominator equal to 0. X minus 3 equals 0 means x equals 3. And that's the other cut point. One of them is special. That's the 3 right here. This one is the excluded value. Just to emphasize it, I'll write it this way. X minus 3 really could not equal to 0. That's forbidden. So we really had x's cannot ever be 3. So I'll write the not equals there. So 3 cut points this time. This addresses the question from earlier. That means we need 4 test values because we'll have 4 regions altogether. Any questions at the moment? Just getting the test points? Okay, let's put this together. We now have a number line extending all the way from negative infinity to positive infinity, all real numbers. We have to plot in these values. And sometimes when I practice these problems, I do get mixed up because if I go 0, 7, 3, my answers aren't going to look right. So make sure you put them in order, even if they're out of order here as a cut points. It goes 0, 3, 7. Now we have 4 regions to test. This one's infinitely long, 2 finite regions, and another infinitely long region. So we'll test 4 different regions out. Because there's nothing to a power 2 or a power 4 to any even power, I'm expecting alternating signs. But just for the sake of being ultra careful and making sure we didn't make any weird mistakes, let's test out all 4 regions. So here are the test points. Way out here, notice we can't use 0 anymore. A cut point can never be used as a test point, unfortunately, but that's okay, we'll live with that. Next best value would be maybe, say, a -1. Set x equals -1. It's going to be -1 right here. But now it substitutes into 3 different positions. We'll have negative of -1, -1 minus 7, divide by -1 minus 3. So now it's kind of like a negative sign hell. Let's work this out carefully. The double negatives right by the red dot cancel to make a +1. So this is just 1 times -8. The denominator, -1 minus 3, gives us a -4. So this is a negative dividing into a negative. The whole result is positive on that region. So we get positive here, and now we just check the next region. If everything is going according to plan, we're expecting this one to be negative. Let's see if that expectation holds. Pick x equals +1, just the easiest value to work with. Then over here, you'll have a -1 multiplying 1 minus 7, but that's just a -6. Divide by 1 minus 3, but that would just be a -2. And that's 3 negative signs. With 3 negative signs, these cancel in pairs, leaving 1 negative sign. So the whole thing is negative, less than 0. So we get negative in that region. Next, probably 4 is a good choice. 5, 6 would do. We just can't use 7. You could use 3.1 if you really wanted to, but I feel like that's working harder than you need to. Integers are usually easier to simplify with. So now we're picking a 4 here. If x equals 4, this thing turns into -4. 4 minus 7 is what we would get here, so that's going to be a -3. 4 minus 3 is going to give us a +1. That means it's just a negative times a negative. This whole thing is just a +12. Or greater than 0 is the whole punchline. What we wanted was the sign. We're less worried about the actual integer we get. So positive in that region, and almost done. Next value, 10 is sometimes a convenient value, but 8 would do the job on this one. Pick x equals 8. And you would have -8 on this one. This is 8 minus 7, so +1. And then 8 minus 5, or excuse me, 8 minus 3 would give us +5. And this is just a negative value, -8/5. The whole thing is negative, less than 0. So negative in this region. So there it is, the entire sign chart. The signs are alternating. I believe for pretty much all the problems in this section, they would alternate. But if you're taking pre-calculus 1, that whole pattern breaks down. Things can double up. You can get negative, negative, positive, positive. Lots of weird things can happen. Oftentimes, the best practice, especially if you have the time, is just to test out all the regions, make sure things are working the way they expect. If you're short on time, say you're doing this as an exam-free problem, they would alternate is a pretty reasonable expectation. Coming back here, though, this is where we finalize the problem. Because it says greater than 0, greater than or equal to 0, it means we want positive regions. So that's the whole punchline to our sign chart. Wherever things are positive are the things we'll take. Greater than or equal to 0 also means we'll be putting solid dots on most things, just not on the 3 because it's an excluded value. So just getting that one out of the way, excluded value means an open circle goes on that one, but 0 is a solution. So we'll put a solid dot here. And same for 7. That one also gets a solid dot. The direction that we shade is in the direction of the positive regions. So we go this way to the left, up to including the 0. We skip this one because of the negative. This one's the next positive region, so we shade from 3 all the way up to 7. At this stage, we've got the graph. All we need to do is transfer it down to interval notation. But the next reminder about interval notation is it's just a paraphrase. You'd start off going left to right, write it down in the exact order you have your graph. It goes from -infinity. The shading part just turns into a comma. Right here at 0, we put in a bracket to match up the solid dot. If we skip a region, we just use union to say this set together with the next set. The open circle means we start off with the parenthesis, but let's use this color just as a reminder. Excluded value means we throw away 3. It can't be a solution. And we go from 3, comma for the actual shading, all the way up to 7, where it closes with a bracket, thanks to that solid dot. So our cut values go in those three spots, and the parenthesis is only because we had an excluded value right on 3. So this is kind of the worst case problem, I would say, that you would do in the homework. It's kind of worse than what would really be a real exam question. But these are good to practice just for the sake of just seeing how this method would carry over into other problems. And if you know you're taking a lot of math, you know, this kind of stuff is really a big technique that you would be using in pre-calculus 1. This is used in calculus 1 for optimization, finding where something attains a maximum or a minimum. So this is kind of one of those major algebraic techniques that you're just going to use over and over again the more math classes you take. But any last questions at all, folks, before we close out this section? Okay, and congratulations also. We complete section 7.6, so that means we made it through chapter 7. Chapter 7 is intense because the moment fractions are on the table, rational expressions, you've noticed the algebra gets pretty hairy quick. So a lot of people kind of like going into chapter 8 for that reason. It's kind of like a break from doing some pretty intense work into doing something a little bit different. The thing that's a little bit different is we're going into radical expressions. That means cube roots, square roots, fourth roots, and so on. Chapter 8 is kind of a major stopway point before we go into chapter 9 and start using tools like the quadratic formula. We're getting back to solving polynomial equations. But the quadratic formula involves a square root already on its own. And so talking about roots is just the natural next stopping point in our algebra course. We'll see a lot of stuff in chapter 8. It's a pretty big chapter. It's going to culminate in solving radical equations, so equations with a square root or a cube root inside of it. And it even takes a tour into getting into exponent laws. So we'll have an opportunity to re-practice our exponent laws again in chapter 8. It starts off with a kind of a soft topic. If we're talking about expressions with roots, we
What's
might as
a
well.
principal square?
Well, the principal square root is where you do something kind of like this. You go a symbol like that and put in the number 25. It's kind of the opposite of what we're doing in part A. Part A says find the square roots, but that's plural. And that's a really weird thing in a math class. Usually, if you're trying to do something, you expect one unique answer. That's where the principal square root comes in. Principal in this context means the really important one, the one that we want to focus on. And you get to say the principal square root, giving you a unique answer. And that's kind of how the note starts. First, we talk about square roots of numbers. Then we immediately say we want to take one root altogether, the principal one. And we use this little symbol here, the radical sign, to indicate it. Other questions at the moment? Okay, let's first start off with this stopping point. Find the square roots of 25. This is not a problem we'll do a lot, but it's a natural thing to answer what is a principal square root, the one we'll do more often down below. So to find the square roots of 25, there's really two answers. The quick one is 5. And the quick check to that is 5 is a square root of 25 because if you take 5 to the power of 2, square root means in our check we're using power 2, you get the thing we started with, 25. But there's another answer. Anyone see what the other answer is for a square root of 25? So 5 and something else are the square roots of 25. Let's pause for a moment to think about it. Any volunteers for a wild guess at the Other square root of 25?
5?
Well, that's the first one that we had right here.
Oh.
But there's a number different from 5 that's also a square root of 25. Here's a big hint. Think of what the check would look like. Whatever goes here where the question mark is, you'd raise it to the power of 2, and you have to get a 25. That's why 5, like you said, is an answer, because 5 squared is 25. But here's the other one that works. 5 and -5, that's also a square root of 25. Reason for that is if you take -5 and you also square that one, that's just -5 times -5, it also comes out as a positive 25. And this is a humongous problem in mathematics. If you just say the square roots of a number, you would probably have 2 answers to that number. We need to fix that. We want to have one root, one answer to this process. And that gets back to the question that you asked at the start of the notes, Clay. That's what the principal square root is all about. So if there are 2 candidates for answers, a positive 5 and a -5, historically in mathematics, people decided we want to pick the answer we like the best. That'd be the positive. Everyone likes positive numbers better than negative numbers. And so the principal square root is the positive root. Let's write this down here on the notes. The principal root, let's say the principal square root, is the positive root. And we indicate the principal square root, like we said, whenever we put in the square root symbol. So that radicand sign there is saying, now take the square root of 25, but we mean the value that comes out as 5 itself. We're ignoring the -5, even though it does check here correctly. We want just the unique answer, the positive value. So anytime an even root comes out, we're always going to go for the positive value, like we did on this problem. So that's our warm-up to Chapter 8 before we look into the next ideas and concepts. Any questions at the moment, thinking about this one? Okay, the principal square root, it's not always as big of a deal because if the index is odd, if you're taking a cube root or if you're taking a 5th root and so on, there's one answer already. The problem only comes up whenever you're taking an even root, a square root, a 4th root, a 6th root, and so on. So here's what the formulas look like altogether. Here we're defining a lot of things all at once. Let me make this thing a little bit bigger. We're taking the nth roots of numbers A. N is what we refer to as the index. So n is the index. It's the number that goes right here.
Ooh, I know A.
Sorry, say again?
I know A on the example 1. Would it be 9 and -9?
Well, not on this one any longer, because if we use that symbol right there, it's kind of like what we're doing on this one. We're talking about the square root, the principal square root. So we'd only have the one answer, just a 9. So this one right here would come out as just 9. Does that make sense on this one here? Okay, so when we look into this overall expression right here, nth root of A, it means n itself is the index, and that means this one's kind of a weird looking thing. The index wasn't written in, but there's an overall assumption. If you write square root 81, we're only going for the positive answer, the 9. But if we were to write in the index is always 2. So this is the one exception. If nothing's put in here, and this is often how square roots are written, it's implying an index of 2 in this problem. The A itself has an interesting name as well. The A that goes inside here is called the radicand. And I looked this up the other day. It turns out this comes from, I believe this was Latin. So we took Latin words and just put them together. This is coming from Latin, basically saying the thing you're going to take a root of. So they just made it a whole word, called it the radicand. Kind of a funny word, but it does come up in the notes. It comes up in the reading. So it's a good thing to just be familiar with. I'm not going to give you an exam question saying, what's the radicand? But if you hear me say radicand, you'll know the thing inside the rational expression. And like we were mentioning before, we have to be really careful, like just in this problem right here. If n is even, then the nth root of a is the principal root of a, so just one answer. On square root 81 here, this does have an even index. We just don't typically write it in. The index is 2, and so it just had the unique answer, positive 9. So that's the rundown of what we're doing so far with the roots. And there's a lot of little tricky concepts that go along with this that we have to be very careful of. Section 8.1 is kind of like again, kind of a warm-up section, get everyone on the same page section. Before we do those kind of trickier problems, simplifying square roots, solving square root equations later on in chapter 8. But that's one down so far. Let's scroll for a little bit. Any questions with the overall definition here or the problem that we just solved? Okay, this part we didn't really say anything about, but this is really important as well. This right here is the check. And it's rare in algebra to have an extremely fast check, but for these kinds of problems, there is one. So it's something we should take advantage of. If you say the nth root of a is b, or say the square root of 81 is 9 in this case, that just means your answer to the power of the index is the radicand. The radicand being a, like we color-coded on the other ones. So even though there's no 2 there, a 2 is implied. It's a square root, and the check is 9 to the power of 2 comes out as the radicand 81. Let me color code this a little bit differently so it looks like the formula above. The check is fast and the work is over on this one step. So again, kind of fun problems. They're not huge, gigantic problems like in chapter 7, but they are tricky. And we'll see what's going on with part B, square root of negative 81. I mean, it seems like it's just like the last problem, right? Let's imagine that we had an idea of what the number could be. We might see a negative sign here and decide maybe the answer is a negative 9. But for that to be a right answer, it has to survive the check, just like the one that's written up here on the notes. The check would look like this. Take something to the power of 2, and it has to, no matter what, come out as a negative 81. And we could try all sorts of things. If we try, say, positive 9, that absolutely doesn't work, right? 9 squared is 9 times 9. It's a positive 81, so this doesn't work at all. If you try a negative 9, that also doesn't work because negative 9 times negative 9 is positive 81. We'll never get a negative 81. It doesn't matter what you put inside here. If all you're using is real numbers, the square of any real number is at minimum 0, but that's when you put a 0 inside there. Any other number you put in, it just gets bigger and bigger. You'll never hit a negative, and you know it's kind of like looking into these equations. Absolute value of x minus 3 equals negative 4 has no solution because the result of an absolute value is just a positive quantity. Same kind of idea over here. If you take an even root, we're talking about the principal square root. Let's rewind. The principal square root is the positive answer. And there's no way to get a positive answer if you start off with something negative on the inside. So that's where these part of the notes come into play. Some of the times you're going to be doing problems in the Newton homework system in section 8.1, and you'll have the option to put in not a real number. And this is one of those times. We'll say for this one, due to the negative sign, that's the whole problem right there. It's not a real number. And that's a funny way to say it. You know, we might have said undefined, but that's not right for this class either, because there is a number that works. It's just not a real number. Later on, we're going to define a new kind of number called, you might have heard things called imaginary numbers or complex numbers is a synonym. Those are the numbers that would make something like this work out. They could actually solve this equation if we just put in the right thing here, but it's not a real number. And the big takeaway is the even root of a negative number is also not a real number. That deserves kind of just a write-up. Let's put this here. The even root of a negative number is not a real number. So if you write out nth root of anything negative, this is not a real number. But remember, that's only when the index is even, so it's not a real number, when n is even. So already square roots are kind of weird. And this course or this section is not just about the square roots. We're also looking into the cube roots, the fourth roots, fifth roots, and so on. And so here's the next challenging problem. This one is a cube root of negative 343. That requires some calculator work. But the fact that it's negative is actually not a problem this time because the index is odd. So this changes the whole game on this one. The check is still the same though. The check always looks like this. Whatever number you come up with for an answer, the check is going to be taking that answer to the power of 3, and it needs to come out as negative 343. So this one does have an answer, even though the radicand this time is negative. And to support this, calculator is a good idea for these kind of problems. Good call, Tracy. This one would come out as a negative 7. Notice sometimes working backwards, coming up with the check first is the easiest way to do this one. In the calculator, you take negative 7 to the power of 3, you get to negative 343. That's where it has to come out as. So that means, just like Tracy said, negative 7 here does the job. So the answer to this whole thing is a negative 7. So that's just the check below. The answer you'd report to, say, the Newton homework alt system would just be the negative 7 itself. The check always involves whatever the index is raised to that power, with a reminder if there's nothing there, it's a square root, so the power's 2. Well, these are tricky problems already. If you look at parts A, we got a principal root of just the positive 9. B is not a real number because the radicand is negative and the index is an even 2. And 3 is a real number. It has a unique solution of negative 7. It works out because the index is odd. The odd indexes are the easy ones. There's no trick questions whatsoever with the odd index. And there's only one root ever. We don't even need the concept of a principal root. There's just only one way to make the negative come out. You had to pick a negative 7. Let's do another one just for the sake of practice. It looks like we're going to do a couple more. Part D is trickier still because we're at this stage getting hyper sensitive to where the negative sign is. The negative sign is on the inside. That was the whole problem with part B. But this one's different. The negative sign is on the outside. This whole thing you're looking at is nothing but a shorthand for negative 1, times the fourth root of 16. In other words, that negative doesn't cause a problem whatsoever on this. For the fourth root of 16, we take 2 to the power 4 and get a 16 out. That's because 2 times 2 is 4, times 2 is 8, times 2 again, power 4 gives us the 16. And so the answer for just this part is -1 times 2. So the whole answer on this is just a -2. So the takeaway in part D is, if the negative is on the outside, it didn't matter that we had an even index at all. The answer to this is just take negative times the answer to the root. 4th root of 16 came out as 2, so the whole answer on this one is a -2. So when the index is even and the negative is on the inside, that's when we have the problem of it's not a real number. Well, last one is 5th root of 32. But if we look into the check, we would take 2 to the power 5. That's just multiplying this one more time by 2. 16 times 2 is 32. So last problem is not quite a trick problem, just extra practice. The 5th root of 32 is 2, because if you take 2 to the 5th power, that's the index, you get 32 out of that. The 32 is the radicand, and so that's how they all go together. It is a tricky process because there's lots of moving parts. My suggestion is when you practice these kind of problems, always do the check, because you're putting two things together in your mind. And I mean, it's also a check, so that's really helpful as well to determining if you have the right answer. Next batch of problems go a little bit differently. We'll probably finish off the next batch when we come back on our Tuesday's class next week. But any questions or comments at the moment? Okay, let's take a look into this next formula, which is interesting. This is leading into the concept of simplifying square roots that we're going to be doing in the next sections, 8.1, 8.2, 8.3, and so on. And simplifying a square root kind of boils down to these two different formulas. It's a kind of cancellation property. The nth root of a to the power of n is just a, but if the index is ever even, we have to just throw in the absolute value of a to make it work out. And there's a couple quick examples we can do just to see how it works. For example, if we're taking, first one is for an odd index. So let's say we're taking the cube root of 4 to the power 3. Well, there's a couple ways you could do this one. The formula says it should just be 4, that the power here, the index here, divides into the power, just giving us a 4. But if you did order of operations on this thing, here's what it would be on the next step. This would be the cube root of 4 to the power 3 is 4 times 4, which is 16, times 4, which is 64. But that just means the cube root of 64 is 4. The check is, once again, raise 4 to the power of the index, which is 3. Let me try again. We get the 64. But it looks like we really didn't have to do that, right? That middle step was kind of just not really necessary. The big idea with the new theorem we're looking into is that there's a cancellation. The index actually divides into the power, and the cancellation goes like this, giving us just the 4. And that's a really nice principle to have, which makes this one a little bit trickier. There's always issues with even indexes. The index is the end there. When it's odd, no trick questions. There's just a clean cancellation. You just get a out. But if the index is even, here's where we run into problems. I think this actually came up in the notes way, way back in the day in chapter 2. So while we're thinking of this formula here with absolute values, here's where it came up way back in the day. This feels like a really, really long time ago at this point. This was the very first section of the course, week 1 of the semester. And we mentioned when we took a square root of this c right here, we only put in 61, but in general, we had to be careful because the square root of x squared is actually the absolute value of x. This is the same kind of formula, but it's also more general. This happens if it's the 4th root or if it's the 6th root and so on. If the index is even, and we take the nth root of a to the power of n, we get the absolute value of a. And that might require just a quick example to justify why is absolute value of a occurring there. It could come up because of problems might look like this. Maybe we're taking, say, the square root of -4 squared. Well, this is a problematic problem because the answer to a square root, here's the next idea, it's never negative. This is a principal square root. It's only going to give us the positive answer. So this principal square root of a is bigger than or equal to 0. This cannot come out as a -4. So what's going on with this one is it's really equal to the absolute value of -4. This one comes out as a +4. That's where the absolute values are occurring right here. If we didn't put in the absolute values and we said our answer was -4, we would have violated this idea. Or another way to look into it is the square root of -4 squared. If we did order of operations on this one, we would square -4. It would become the square root of 16, and the square root of 16 is 4 itself. Either way you look into it, you get a +4. The absolute values right here are just a way to ensure your answer really does come out positive. And that's not as big of a deal if you know what the values are, like the -4 we wrote in. But it is a huge deal if you're dealing with a variable x. Now we don't know if x is positive or negative. We really do have to put absolute values on some of these. These go pretty quick in general, though. On part A, the index is odd. So this 5 out here divides into the 5 there, and you're left with just x. Our work is completely done at that step. The one down below is the tricky one. The index is an even 6. So this 6 divides into the power of 6 over here, and we're left with absolute value of x. Absolute values are really easy to forget on these kind of problems, but they come in because of the idea we saw in this example below. The answer can never be negative, so we force it positive by throwing absolute values on it. Well, we have several more that we want to take a look into, but I wouldn't want to rush through them in the last 3 minutes of the class. So we'll make this part B be our last problem. Any questions on how this theorem connected with parts A, part B? Yeah, for exam 2 grading, I'm going to be grading them on Friday, and I should be done sometime Friday, I'd say before 6 o'clock. So I'll be mailing you your graded exam 2 to your ISU email address. Probably sooner than 6 o'clock, but that'd be kind of my latest estimate on that. Other questions at the moment? You bet. Thank you. Okay, well, have a great weekend, folks. Have a great night. We'll be back to this section 8.1, 8.2, 8.3 when we come back next Tuesday.